So whether it's in an applied calculus class or the regular calculus sequence, you learn the chain rule, but you also learn patterns. The chain rule shows up in the same form again and again and again, and eventually you get to the point where you just use it mechanically. And the material of this section is just the chain rule, applied to a specific type of function. The textbook calls it something like the general power rule. And it says that if you've got the derivative of a function raised to a power, it's the power times the function to the power minus 1 multiplied by the derivative of the function. And this is the chain. What we have here, where the n comes down and then we subtract 1, this is the derivative of the outside function. We have the inside function stuck inside of it, and then we multiply by the derivative of the inside function. But by memorizing this, now you can see a problem like this. You can see f of x equals x squared plus 7x minus 2 to the third power. And if you want its derivative, instead of pausing and going, okay, what's the outside function? What's the inside function? You say, well, we have a function raised to a power. We use the power rule, essentially. We leave this quadratic alone. We reduce the power by 1. So we're just using the power rule. And then we multiply by the derivative of this quadratic. 2x plus 7. And there's the derivative. No muss, no fuss, no messing around trying to figure out what the inside and outside functions are. It just is very mechanical, which is often nice. It's often nice to not have to think about a lot of things and just proceed mechanically. Another example, let's put in a constant multiple just for kicks. 2 times the square root of 5x minus 1. Let's take the derivative of this. We've hopefully internalized the idea that square roots are just powers. So when we take the derivative using the generalized power rule, what should happen? Well, unrelated to the generalized power rule, but just how constants work, the 2 sticks around. So the 2 stays there. Then the generalized power rule. The power ought to come down. The 1/2 ought to come down. We leave the function inside the power alone. We subtract 1 from the power, negative 1/2. And then we multiply by the derivative of the thing inside the power. The derivative of 5x minus 1 is 5. And if we rewrite this a little, of course, the 2 times the 1/2 is 1. And we get 5 over the square root of 5x minus 1. And again, this is really the chain rule, but we're not messing around thinking about inside and outside functions. We're just thinking that we have an expression, this 5x minus 1 raised to a power, and we're using this version of the power. I guess plenty of examples in the textbook and on Canvas, so I try not to sort of do an overwhelming number of examples in these videos. But h of x equals 2 divided by x squared plus x plus 1. We don't need the chain rule for this. This is a quotient. We could use the quotient rule. Often when we just have a constant in the numerator, though, we find it more convenient to rewrite division as a power. This is 2 times x squared plus x plus 1 to the negative first power. And why do I say this is more convenient? Well, because the quotient rule is messy, right? The quotient rule that u over v prime equals u prime v minus uv prime over v squared. That's about as messy a rule as we have in this course. Whereas if we rewrite this, now we just have a constant times a power, and it basically turns into the last example. How would we differentiate this? The 2's a constant. It stays put. The negative 1 comes down. We leave the function alone. The quadratic is still x squared plus x minus 1. We subtract 1 in the power. Negative 1 becomes negative 2. And then we multiply by the derivative of this expression by 2x plus 1. And if we rewrote this, negative 2 times 2x plus 1 divided by x squared plus x plus 1 squared. And this is precisely what you'd get using the quotient rule, but it's maybe simpler than the quotient rule.